So my talk is devoted to some connection between different approaches to knot theory. As you know, originally a knot is defined as an embedding of the circle into the three-dimensional space. And we consider such embeddings up to isotopies. And this is a topological approach, original. On the other hand, Redemaster noted that knots can be described by diagrams, and we can define knots as equivalence classes of diagrams modular the Redemaster moves. So there are three Redemaster moves, as you know. And if one speaks about, for example, knot invariance, there are a number of invariants which are defined from topology, such as, for example, knot group and the fundamental group of the complement of the knot, and some other invariants, hyperbolic volume of hyperbolic knots, and so on. On the other hand, we have many invariants which are defined combinatorially. For example, the linking number, one of the simplest invariants of links, and one of homology. The original construction was purely combinatorial. So the aim of my talk is to establish one connection between these two approaches. So let us look at a diagram. If we consider combinatorial approaches to knot theory, then we deal with diagrams, and any diagram consists of elements, and we can look at arcs that is part of the diagram of the knot between two undercrossings. We can look at semi-arcs, which are just edges of the diagram. Consider it as a following graph. The vertices of the graph are crossings, and there are regions which are connected component of the complement to the diagram. And each diagram can assign to each diagram the set of its arcs, semi-arcs, crossings, and regions. And then if you consider a combinatorial invariant, you use these sets to construct some value, some invariant value, or polynomial, and some other things. Let us consider a typical combinatorial invariant called linking number. So we take a two-component link, and then just take the sum of the signs of its crossings, but not of all crossings, of those crossings which are intersection points of two different components. So if you look at the formula of the linking number, you will see that it uses two types of labels of crossings. On one hand, we we distinguish between self-crossings of one component and mixed crossings. And on the other hand, we have the sign of the crossing. And if you look at these characteristics of a crossing, you can see that these labels are invariant under Rademaster moves. So, and if you look at other knot invariants, like, for example, quandles, quandle covariance, and some index polynomials, you see that the construction also uses some labels of arcs or semi-arcs or regions. So we can ask the question which labels we can use in the construction of knot invariants. Which invariant labels of diagram elements of crossings and arcs. What do I mean by invariance? So if we have some diagram element, for example, an arc, and apply a random move, this arc transforms. It may split into two arcs, or some arcs may merge, or an arc may disappear. Between two diagrams before and after the ready master move, we have arcs which are correspondence between arcs of these two diagrams. And we say that we label each arc by some element of some set, and we assume that the elements which are assigned to these red arcs on the left and the right diagram must be the same. So the question is to describe possible invariant labels of arcs or crossings if we consider crossings. And if we ask which information can carry these invariant labels, we come to the universal invariant labels, which are initial object in this among all the labels. And it is natural to define these invariant labels as equivalent classes of these diagram elements of arcs. So we consider all diagrams, and then we identify the arcs of different diagrams which correspond to each other by the Redomasty move or by some isotopy of diagram. And the set of these equivalence classes is exactly the invariant, the universal invariant label. So the question is how to describe this set of equivalence classes. And this set of equivalence classes of arcs for all diagrams of one node can be called arcs of the node. So we deal with all diagrams, and we assign these arcs of these equivalence classes to the node itself. Analogously, we can consider sets of semi-arcs of nodes and regions of nodes. And this means we consider all these equivalence classes of, for example, regions among all diagrams of the node. So the question is how to describe these sets. And the conceptual answer to this question you can see in this slide. For example, if we consider arcs, we can code each arc by so-called probe, a path from the, so we consider nodes in some thickened surface F. So we consider the top boundary of this thickened surface and connect it with a point on the arc. And this probe, this pointer, this probe points out on this arc. And the isotopy classes of all these paths from the top to the node are exactly the set of invariant labels. Analogously, we can code a region by a path from top to bottom, which doesn't intersect the node, like this. And there are analogous descriptions for semi-crossings and crossings, semi-arcs and crossings. To be more precise, the isotopy classes of such paths are not universal invariant of arcs and crossings, but they are universal co-invariant. What do I mean by co-invariant? If you look at node invariance, you can note that we can split this set of invariants into two groups. The first invariant is is invariants which are the pure invariants of nodes, something which doesn't change when we pass from one diagram of node to another diagram, from one node to an isotopic node. For example, if we have a numerical invariant or polynomial invariant, this polynomial is one and the same for all diagrams where we calculate, where we compute this, for example, Alexander and John's polynomial of a node. On the other hand, if we consider, for example, a node group, formally for different nodes which differ by anisotropy, the node groups as the fundamental group to the complement to the node will be different by their isomorphic. So there is a group of invariants which are defined up to isomorphism, and I call this group covariance. And there are several constructions to pass from invariance to covariance, and this area is called categorization of a node invariance. For example, we pass from polynomial invariant, like John's polynomial, to Chalanov homology. So, in fact, what is you can see here, the isotopic classes of these curves, of these paths, are universal co-invariants of arcs and crossings and so on. So let us pass to formal definitions. A formal definition of difference between invariance and covariance can be formulated as follows. Assume we have a category of diagrams, of node diagrams, D, and then an invariant is just a functor from this diagram category to some other small category, such that each morphism, which is Rydemasters or isotopy, becomes after this functor an identity map. This means we map all diagrams of the same nodes maps to one thing. And the co-invariant is a functor from the diagram category to some other category, such that the image of each morphism under this functor is isomorphism. And an example of such a co-invariant is, for example, quantum covariance, when we assign to each diagram the set of covariance by some quantum Q. And for diagrams which differ by Rydemasters, we have an isomorphism between the sets of covariance. So this is a co-invariant. And invariants are just, if we have invariant in this categorical sense, it means that then we have usual invariants in the usual sense with values in the object set of this small category C. And now let us define the category of node diagrams. In fact, I will consider tangles in a thickened surface. Consider an oriented compact connected surface F, and then a tangle is an embedding of one-dimensional oriented compact manifold to the thickening of the surface F. Some embedding this. And then if we have a projection, the projection from thickening to the surface, and the image of by this projection of a tangle is called a tangle diagram. In fact, we consider a tangle in general position, and this projection from F times interval to the surface F, in fact, induces a stratification of the set of tangles. So we have the set of tangles of embeddings, and then the first stratum is the tangles in general position. This means the projection of a tangle is a has only double points. It's the usual diagram of a knot, a link of a tangle. But if we consider families of tangles, family of embeddings, we can encounter tangles with one singular points. There are three single points of codimension 1, a cusp, a tangency, and a triple point, and each of them corresponds to a ready master move. And then the second stratum is includes single points of codimension 2. There are 5 points of single points of codimension 2, and or maybe it may includes 2 different points of codimension 1. So, so we have the following rectification, and then we can define a category of tangle diagrams. I consider 4 categories. This category split into combinatorial categories and topological categories. And the object of combinatorial categories are tangle diagrams, and the object of topological categories are tangles in general position. And combinatorial topological categories also are divided into a strict category and homotic category. A strict combinatorial category is just tangle diagrams with morphism, which are sequences of ready master moves. And we just take a formal composition of ready master move, and then concatenation of these sequences gives us some category. And this category is equivalent to some topological category whose object are tangles and morphism are sigma 1 transversal isotopies. Consider it up to isotopy, up to homotopy in these isotopies. Sigma 1 transversal means we encounter only usual ready master moves when we pass from one embedding to another embedding. And if we admit if we consider all isotopies, all possible isotopies between two tangles, then we get a so-called homotopy topological category, and this category is equivalent to some combinatorial homotopy category, whose object are diagrams and morphism are sequences of ready master moves modulo some relations. There are contraction relation. If we have increasing and decreasing ready master move, we identify this composition with the identity. There are far commutativity relations and some relations which produced by singular points of codimension 2. So there are 5 singularities of codimension 2, and the deformation of these singular points produces some cycles, some sequences of ready master moves. For example, if we have a quadruple point, then we have this cycle of ready master moves, of third ready master moves, and we assume this composition, this cycle is equal to the identity. And other points, for example, this triple tangency point also give some cycles which are identified with identity morphisms. So we defined these categories, and then what are arcs and crossings in this categorical picture. So if we have a diagram, then we can assign the set of arcs and the set of crossings to this diagram. So we have this correspondence from diagrams. We have some set of diagram elements, and this correspondence, in fact, is a functor from the strict combinatorial category to the category of relations. If we have a morphism morphism is either an isotopy or a Redemaster move. For an isotopy, we have a bijection between the sets of arcs and crossings and regions of these two diagrams connected by an isotopy, by diagram isotopy. And then we have a bijection. And if we have a Redemaster move, then now we define this morphism, the image of this morphism by the functor as a correspondence between two diagram elements in one diagram in the other diagram, which have common points outside the disk where the move occurs. This means if we have some small element which disappear in the move, then this element corresponds to nothing. And here you can see an example. Let us consider a first Redemaster move. Then we have here originally one arc A, two regions, one semi-arc, and after the move, we have two arcs A prime, A1 prime, A2 prime. So this arc A corresponds to these two arcs. We have the following correspondence. And if we, for example, consider the inverse Redemaster move, then, for example, this small region R3 prime disappear during the move, so it corresponds to nothing here. So we have the following, and we have this crossing. After the move, it corresponds to nothing. So we have this functor image of the morphism by the functor. So we have some functors, and then in order to define a universal invariance and co-invariance, we introduce the following relations. The first relation is affinity. Affinity. If we have two diagram elements in one diagram, one and the same diagram, and then we say they are affined if after some Redemaster move, the sequence Redemaster move, these elements merges. These elements merge to one element. In this case, we say they are affined, and one can check that this relation is affinity relation is reflexive and symmetric, but not transitive. And its transitive closure gives the equivalence relation called strong equivalence. So it's defined as follows. So if we have a pair of equivalent elements, then the image after some morphism of these equivalent elements must be also equivalent. And strong equivalence element equivalence is equivalence for elements of one diagram. And then we have also a weak equivalence, which includes elements of all diagrams. So we say that if we have, for example, a crossing and apply some Redemaster move and get other crossing of other diagram, we say that the original crossing and the crossing on in the other diagram are weakly equivalent. And here you can see an example. On the right, we have a picture of strong equivalence. For example, if we consider these two arcs, define equivalence on the arcs, for example, then after this Redemaster move, second Redemaster move, this arcs merges to one arc. So they are affined, and then they are strongly equivalent. On the other hand, the middle arc and the right arc are also affined and strongly equivalent. This means that all three arcs in the middle picture are strongly equivalent. by analogously arcs here, two couch arcs are equivalent, strongly equivalent, and on the bottom picture, these two arcs are strongly equivalent, but there is no equivalence between arcs in the bottom diagram and middle diagram because they are different diagrams, and strong equivalents are defined only within one concrete diagram. But if we consider the weak equivalence, all these red arcs are equivalent. So we have the following equivalence. And in fact, the equivalence classes, weak equivalence classes, give us the universal invariant of arcs in this case, and other elements in other cases. So we must describe somehow these equivalence relations. And let us see how one can do it in the case of arcs. So assume we have a tangle in general, and its diagram, its projection, and then we have some arcs on the diagram, and we can construct two each arc. We can take a point on each arc and connect it vertically with the top boundary of the thickened surface. What we'll get is called the vertical arc probe of this arc. And if you consider all a path from top boundary to the node, we get what is called arc probe. Arc probe. So we have vertical arcs, which corresponds to arcs of the diagram, and some arc probes, which don't correspond to anything. And it appears that we can describe these combinatorial relations using these probes. For example, we have the following the following proposition. If we have two arcs in the diagram, if they are affine, only if the corresponding arc probes, vertical arc probes, bounds a square, an embedded square. So we have a square whose sides are these vertical probes. So we have some side on the top boundary of the thickened surface, and the bottom part of the disk goes in the knot, in the tangle. So we have the following disk, and so we reformulate this combinatorial condition by one topological condition that two probes bounds an embedded disk. And then we can extend this relation to any pair of probes. We say that the pair of probes, if they bound a disk, then they are topologically affine. Okay. Then one can so one can show that this relation is not transitive, and if one consider the transitive closure, then it appears that the transitive closure of this topological affineness is isotopy between arc probes. So we have the following corollary: two arcs are strongly equivalent only if the correspondent probes are isotopic. And this leads to the following definition of theorem. Let us consider a tangle and all isotopic classes of arc probes of this tangle. Then we have some set, and this set is the universal coinvariant of arcs. So any coinvariant label defined up to isomorphism comes from this set. a set of isotopic classes of arc probes. And if you want to define not co-invariant by invariant, universal invariant of arcs, then you should consider the motion group. In general, if we have a submanifold in a manifold, then a motion is an isotopy of this large manifold M, such that the initial position and the final position of the isotopy of N is N. And if at each time N, the position of N coincides with the N, then we have a stationary motion, and the quotient of all motions by stationary motions are the motion group of the submanifold. And then we consider the motion group of tangle in the thickened surface. This group acts naturally on the probes, on the isotopic classes of these arc probes. And then the quotient by this section is the universal invariant of arcs. And one can see that if we have a classical knot that this action is transitive and the quotient space is 1 point. This means that then a universal invariant of arcs for classical knots is trivial. But universal co-invariant is not trivial because there are quantum covariance, trivial quantum covariance. And analogous construction can be performed for another remark. If we consider a diagram, we have vertical probes and some other probes, and other probes can be considered as arcs which are not exposed. They are implicit arcs, then can be made an arcs of diagram after applying some Reidemeister moves. And in fact, if we consider any set of arc probes, we can make them, we can verticalize them in some diagram. So we can make them arc of some diagram after applying some Reidemeister moves. And then we can do analogous things for regions, semi-arcs, crossings. In the case of crossings, the vertical probe consists of 3 arcs from the top boundary to the node, and path between 2 points of node and to the bottom part, and the middle part is framed. It's framed, and here you can see how one make frames. So one, if you have overcrossing, undercrossing, connect this part with the band as follows. And then if you look at this picture in a 3-dimensional space, you will see the following bands. So we have the following framing. Okay. And the isotopic classes of these probes with the frame part are the universal invariant and co-invariant, the universal co-invariant of crossings, and after factorization by the motion group, you get the universal invariant of crossings. And so these sets of isotopic classes of arc probes, crossing probes are connected by natural maps, because if you have a crossing, you have incident arcs, semi-arcs, incident regions, and on the level of probes, you have the same maps. And maybe I skip this part. There are another, we can consider other functors, for example, mid-crossings, by assuming that the crossing survives after third randomized moves, which move an arc below the crossing or over the crossing. Assume we identify this crossing C and C prime on this picture left on the right picture. Then we get some other functor than the crossing functor. This functor is called mid-crossing functor. And the probes for these mid-crossings are just oriented bands between 2 points on the node. And one can use this mid-crossing to transform the node. So we can smooth the node near this mid-crossing and change overcrossing by undercrossing. So you have this following transformation. And there are several examples where such mid-crossings appear. For example, if you have a splitting of a node into a connected sum, the separating sphere form some mid-crossing on the node. And another situation where mid-crossing appears if you have a ribbon node, a node which spans a disk with the ribbon intersection, and this intersection, if you see, they are mid-crossings. So we can use this mid-crossing to work with these ribbon nodes. And if you consider a universal invariance of arcs, nodes, and links, then the value of this invariance are isotopy classes of embedding of some concrete spatial graphs. For example, arcs are the set, the universal arcs from the set of isotopy classes of embedding of such red graph with a which consists of a circle and some arc probe, the path from circle to the top boundary. And other diagram elements also have representing spatial graphs. And at the end, I say some words about how one can construct invariance using these sets of universal probes, universal invariants. So if we have an invariant label of some diagram elements, for example, crossing with value in G, then if we have a diagram, we have the set of all crossing, for example, and take the values of this G for all the crossings. So you have a multi-set of values, and if G is has additive operation, then you can map this multi-set to G, take the sum of these values. And the value is a diagram sum. Sometimes this sum is invariant under randomized moves, and in this case we say we have a diagram sum invariance. And an example of diagram sum invariant for the crossings are linking coefficient, index polynomials, which use indices and parities, and Quantum cycles invariance. And if you try to do the same for arcs region, then it appears that all invariants, all diagram sum invariants are trivial. So this works only for crossings. Another construction which we can use is global sum invariant. Assume we have some invariant label of crossings, for example. Then we have the set of all crossing of these isotopy classes, and the map from the set of these isotopy classes of probes to this G, because it is an invariant. And then we can take the sum or an integral of this function. The value of this integral is called the global sum. For example, if we take mid-crossing, consider the following example. We distinguish, take the mid-crossing which corresponds to splitting of a knot into direct sum. Then we have a finite number of such mid-crossings, and if we take the sum assigned to this mid-crossing ones and to other mid-crossing zeros, we get the number of components in the prime decomposition of the knot. Take this invariant. And third construction I will consider here a skein invariant. Assume we have some functor, some invariant functor. For example, we take mid-crossings and some invariant of these mid-crossings, and assume we can assign to each this invariant some map to skein relations. So, for example, consider mid-crossing, then we can make some transformation of a diagram of a knot near this mid-crossing and produce some skein relation. For example, Kaufman skein relation or skein relation from Alexander polynomial or Humphrey skein relation. So I can make such a skein relation, and all skein relations form some model. And if we consider free model generated by tangles and take the quotient by this space of skein relation, we get skein model, and projection of tangle to the skein model is a skein invariant. And this is how one can describe the polynomial invariance of knots, like John's polynomial, Alexander polynomial, and Humphrey. So we have such invariance. And so my time is over, so maybe I stop here. Thank you for your attention. Are there any questions?